All right. So I wanted to talk about organic synthesis, and I want to talk about it from a perspective we can understand. All right. And one of the ways to do that is to kind of make it clear about how the reactions we've been studying and how the reactions you studied in part one, how all of that matters, right? And there's some really important synthetic discoveries that have been made that simple, very simple reactions that we've studied in class have been used to do, right? So this is actually uh, a list or a listing of basically all the reactions that you learned in part one, and I'm going to show you how they apply. So, and then anything related to part two, I'll bring that up as well. But these are a bunch of different reactions from part one, right? A lot of them. And again, a lot of part one carries over to part two, right? It's like Lego blocks. What you learn in part one is your foundation for the second part of organic. All right, so we're going to talk about organic synthesis, right? So what is synthesis? It's basically taking specific chemical reactions and using them to create or synthesize a target, right? The target molecule can be anything. And the reason this is important is because there's very few uh, products on the market as it relates to bioactive products or pharmaceutical products that are not synthesized, right? So pharmaceutical companies, they use synthesis for drug design and drug discovery. Industrial chemical companies, they use synthesis towards development of new products, right? You think about a product like, and I know this is probably a terrible example, but a product like Roundup that you use as an herbicide. Well, Roundup has a specific active ingredient that has to be synthesized, right? Sometimes you can derive uh, targets from natural products, but we're going to see in a second, sometimes that's not beneficial as far as for the environment. And then the other part, you just don't get enough. You don't get enough of that compound from natural sources. So you got to have a way to make it. And then in academia, we do synthesis to develop new ways to do existing reactions. Like, again, I always talk about reactions as tools in the toolbox. So academic researchers are always looking to develop new tools to do maybe sometimes the same reaction that's already been done, but a new way to do it. Maybe it's more efficient. Maybe it's more atom economical. Maybe it's faster. Maybe it's less catalyst, less waste, so on and so forth. So for um, as far as synthesis categories, right? You have method development, which is discovery, right? You're trying to develop a new method to do a reaction that's already known, that's already out there, and you're just trying to develop or innovate and develop a new way to do it. The other way is total synthesis, and that is taking complex molecules that already exist and developing a stepwise synthesis to get to them. Now, that word stepwise is not the same as a stepwise mechanism. This is using multiple steps where you might have one step towards a product might be 10 reactions, in a sequence. And then that'll give you one fragment, and then you build up another fragment, so on and so forth. So to do total synthesis, you can do it two ways. You can do it a convergent synthesis, right? That means you build up your fragments, and then uh, at some point during the reaction, you bring those fragments together, right? You converge the fragments. Or you can do a linear synthesis where you start with one simple start material and you keep building on it until you get to uh, the product, right? So convergent synthesis a lot of times is more efficient, but prior to doing something like that, linear synthesis was the way to go. So, all right, and so the biggest part of doing synthesis is planning, right? You have to figure out, you have your target, and you need to figure out how you got there. So if you remember when we talked about uh, granular additions, we talked about uh, Diels-Alder cycloadditions, and we started at the product and worked backwards. Anytime you do a synthesis, you have to do a retrosynthesis. So you start with whatever that molecule is that's your target, and you look for ways to chop it up into pieces and work backwards. And you think forward about how you will make each piece, and then bring those pieces together, right? So I'm gonna give you a simple example, right? Let's say we have this product where we have 2-hexene, and then we want to work backwards and figure out how we can make 2-hexene from 1-pentyne, right? And so there's a way to do that. The way you think in terms of retrosynthesis is you always ask, what is the immediate precursor, right? What molecule came right before my product, right? So if you look at the screen, you can see that if I take a triple bond like this one, right, and hydrogenate it with Lindlar's catalyst, I can get a cis alkene from that, right? Now the question is, where did this come from, right? So then again, you're thinking backwards. The way where the starting material came from was, if you look at the alkyne, you can consider, or you ask the question, how did I get the methyl group on the alkyne? Well, you can do acetylide formation, right? You can take the alkyne, you can deprotonate it with a base, and then you can do a SN2 type substitution with an alkyl halide like methyl iodide to get there. So that's kind of the process. You look at the product, and then you think about what came immediately before that product. And then you look at the start material for the initial reaction and say, oh, well, what came immediately before that? So that's how kind of the thought process behind retrosynthesis. And then if you look at the overall synthesis, you can see what we did. We just combined all the steps. First, you deprotonate with a base, then you add the methyl iodide, and then you treat it with Lindlar's catalyst and under hydrogenation conditions, and boom, you have that product, right? I'm gonna skip this one, and we're gonna move to something more. All right, so now let's think about another molecule, right? This molecule is called Taxol, right? The one over here, this big. We've seen this before when we were studying stereochemistry, right? So this is again, a cancer treatment drug. It was discovered in 1967. And again, every time I talk about this, I think about when my wife, before she passed, this was the first drug that she took when she was diagnosed with breast cancer. This is the first chemotherapeutic that she took, right? This is another point towards why you need synthesis. All right, the way Taxol was discovered, it was isolated from the yew tree, Pacific yew tree, right? So in order to treat one patient, you need 6 trees that are 100 years old, right? Because you're going to take the bark from the tree, scrape it all off, and then extract out the Taxol, right? That's impossible. You're not going to treat very many patients like that. So you need a way to actually make the compound. Now, the question is, and I'm asking this because I want y'all to interrupt or participate. If you look at Taxol, how do you think they knew what the structure of this was based on the extract from the yew tree? Like, what methods could they use to determine that structure? Methods that we've talked about.
What, like NMR?
Yeah, absolutely. You can take an NMR of the extract, And based on the NMR spectra, you can figure out the structure. I know it's complicated. I know it's a huge structure, but you know, if you're an organic chemist, one of your tools in your toolbox is the ability to interpret NMR, very complex NMR spectrum, right? So you could most definitely take an NMR and an infrared, uh, and maybe you don't wouldn't necessarily need UV, but a mass spec would also help because that would help you to identify. You know, this molecule is going to have a specific molecular weight, right? So you can take those techniques and apply them and work from the basically from the NMR spectrum and the mass spec, which will give you the formula. You can take those two things and the infrared and work backwards to figure out the structure, right? Yes, it's very complicated and it has a lot of stereo centers, but you could use the NMR to determine the structure, right? It is again the first time it was synthesized, not discovered, but synthesized in a lab was in 1994. And you had basically two groups competing to make it. The Nicolau group, I think KC Nicolau was at Harvard, and then Robert Holtmann was at Florida State. And so that was this competition to come up with this molecule, right? And I think it took Holtmann like eight years or 12 years, something like that, to actually get a synthesis that was scalable, meaning that you could do it in a factory. All right, so let's think about this from a retrosynthetic standpoint, right? So you got this big giant molecule right here. And then if you look over here, this is a precursor to that molecule. So basically you would chop this thing up right, let me see here, right here. You see can you see the cursor where it's pointing?
Yeah, the ACO.
Yeah. So right here, in between this carbonyl and this acetate group, that's chopped. You can see that right there. And this piece is also chopped off right here. And then you can also, so where did this come from? This is the central part. This is the backbone. Where did this come from? So then you can see again, you chop it here and you got two pieces right here. So these are the fragments that were made and then merged together. So this would be an example of what you call a convergent synthesis, right? You make smaller fragments and then you use certain types of reactions to connect those fragments, right? And then so, hold up. I did not tell you to do that. All right. So all of these fragments have to be made, synthesized with the proper stereochemistry, right? That's very important. So you need reactions that are going to give you that proper stereochemistry. How do you set stereochemistry? Anybody remember from when we first started talking about that? There's only two ways to do it. And you know both of them. It just might not be coming to mind right now. If you want to set a stereo center, how would you do it? One way is to use a chiral catalyst. Is that right? Do you remember that? What's the other way? We studied it too and talked about it and did problems with it. So one way to set a stereo center is to use a chiral catalyst. The other way is to react on something that already has a pre-existing stereo center. Those are your two ways that you set chirality. I can't believe nobody said that. All right, here we go. So this is the Holtmann retrosynthesis. It's a little bit more, less destructive to the backbone, right? You can see here, going from here to here, he just cleaved off this part right here. This uh, linear chain is cleaved off, right? And then going from here to here, right? You can see the uh, the cyclic ether here is not there, right? And you can also see some of the other functional groups are taken off. So he started from this smaller backbone and then kind of worked his way up to Taxol, right? You can see with the Holtmann synthesis, he actually started in 1982 trying to make this molecule. In terms of grad students, that's 1982 to 1994, so that's 12 years. So that's probably 3 grad students, multiple postdocs, and some undergraduate researchers all working on this. So it's definitely, it looks very daunting, but it's not. The way that you approach these things, it's never a solo effort, right? It's always a group. You might have one person who's working on one fragment, one person working on the other fragment, and then every week you sitting down having a meeting, discussing the next steps, discussing how you're gonna converge the fragments together, all of that. All right. So he actually sold the license to his synthesis for to Bristol Myers, and this was several years ago. He had earned up to $200 million, so I know it's way more than that by now. And this is again an example of a linear synthesis. Started with this backbone, and he just added, and then he added, and he added, and he added until he got to the final product, right? So it's different from the Nicolau synthesis, and that is linear, and the approach is different, right? So if you look at the Holtmann synthesis, one of the key steps is to convert this alkene into a diol. All right. Anybody remember that reaction from part 1? All right. It's an osmolation. If you take osmium tetroxide and then sodium hydrogen sulfide, and you treat that double bond with that, it's going to give you a diol with both alcohols cis to one another. All right. And then if you look at the Nicolau synthesis, and I react this alcohol right here, because all these these TBS groups here are what you call protecting groups. They're put in place, they're silicon protecting groups put in place to keep those alcohols from reacting until you need them. All right. But if I took this alcohol and I treated it with a base, that's what potassium hydride is, treated with a strong base and a benzyl halide. What do you think is going to happen there? We just did this reaction, by the way. Not this. Go ahead.
Well, I was going to say the ring is going to attach where that OH is.
So would it be the ring itself?
No, like it's going to replace that BR.
Yes. Good. Who is that?
Juanita's.
Good, good, good. What's the name of that reaction? You're absolutely right. What did I just make? What did I convert the alcohol into in the product? What functional group? It's no longer alcohol, right?
No. Oh. Like a aldehyde.
Look at the structure. You got a carbon on this side, you got a carbon on this side, and oxygen between both of them. It's an ether, right? So this is a type of ether synthesis, which we studied already. We studied Williamson ether synthesis, right? But again, you would think with all of these complicated, molecules with all these stereo centers, that all of the reactions are just so esoteric and so far out, and that's not the case. A lot of the chemistry is simple, acid-based, nucleophile, electrophile chemistry to build up these big, giant, structures. All right. And so let's look at another synthesis, right? This is the structure for cocaine. This is the actual structure. Now, the cocaine itself, when you extract it from the coca leaf, it actually has a HCl molecule. Let me let that go back. It actually has a HCl molecule kind of associated with this nitrogen, right? So it's actually cocaine hydrochloride. That's why when you take the cocaine and you add baking soda to it, which is a base, right? Well, which is basic, you add baking soda to it. When you add the baking soda actually removes the HCl. And so then the cocaine becomes what we know as crack, right? That's why they call it back when they first started doing that back in the early 70s, late 60s, early 70s. They used to call the crack part freebase because what you're literally doing is freeing up the nitrogen in the cocaine hydrochloride extract. So you're freeing up the nitrogen, which is a basic atom, right? So you call it free base. That's why when you get rid of the HCl, the cocaine that you are left with is different because the HCl is no longer there. So you call it free base, right? So the retrosynthesis, the abbreviated retrosynthesis is shown here. And I actually have a handout that I'm going to post to with these steps on it. But this is the abbreviated retrosynthesis, right? So this is cocaine and this is the precursor to it. All right. And so this precursor right here, when you look at the uh, how we get to here, it's actually a really simple acid-base reaction, right? I'm sorry, nucleophile electrophile reaction, where this nitrogen is going to attack methyl iodide and become methylated, right? So you think about this in terms of like real life. This is, this was actually synthesized in a lab by a group, by the Tuffarello group back in 1979. Now, let me say something about synthesizing drugs and synthesizing things that are potentially, how do I put this? Things that you can actually use. Like if you're doing research on THC, you're doing research, they were actually researching this. You're doing research on cocaine, methamphetamines, anything like that. You have to have approval from the DEA. You can't just go in the lab and start making cocaine. You have to actually have approval, and the DEA has a list of chemicals that are used in these different syntheses. And if you buy any one of those chemicals, you're going to get a phone call from, this happened to me before, you're going to get a phone call from the DEA, and they're going to ask you, what are you using this for? What school or where are you in school? If you're a graduate student, what school do you attend? What's your research? They're going to want to know all of that stuff before they would even allow the chemical company that you're ordering from to ship it to you. So it's not just, you can't just go and order all the stuff to make cocaine and then go in the lab and just start making it. The DEA is going to be on your behind. And I forget what I was making. I was working with something as a grad student, and I ordered a compound, and it just so happened to be a precursor to like a morphine synthesis or something like that. And I definitely got a phone call. I had to fill out a lot of paperwork before I could even order a gram of this stuff. I had to fill out a lot of paperwork and things like that. So anytime you're working in the lab and you're working with drugs that can be consumed, what they call maybe, I guess it's Schedule C or whatever it is, then you're going to have to deal with that. So, all right. So here's the initial part of the synthesis, right? It's actually a cycloaddition reaction. If you look right here, you start out with this N oxide, right? And then you treat that with this alkene. So you well not treat it, but react it with this alkene, and you actually do a cycloaddition, right? You have it's what you call a 1,3 dipolar cycloaddition. So it's these three atoms, 1, 2, 3, and it's the dipolar part comes from the charge on nitrogen and the charge on oxygen. So it's these three atoms and then these two atoms here. So you're going to get a 5-member ring as your product, right? Remember, anytime you do cycloaddition, when we did a 4+2, then we got a 6-member ring. So here we're doing a 3+2 cycloaddition, and so you're going to get a 5-member ring as the product. And if you look down here, you can see down here in the mechanism is really similar to the Diels-Alder cycloaddition. Not the same, but it's very similar because the oxygen here, you can see attached this carbon that's partially positive, and then those electrons in the pi bond go to this carbon. So this is your intermediate. This is an intermediate. Now, what do you think is going to happen with this intermediate? Do you think it's going to sit here, or based on the product, what do you think happens next in it with that intermediate?
I would say that carbon breaks off and then the oxygen. Well,
Go ahead. I think you were on the right track.
so the carbon will break off and I don't know, that functional group will somehow, I don't know, reattach, but
So let's look at the product. This is the product, right? This is the oxygen, right? This is one of your carbon, excuse me, and this is the other carbon that's negative. You can see from the product that it's going to cyclize, right? And so this carbon right here, look at the two atoms over here, the carbon and the nitrogen. That nitrogen has a plus charge. So there's a big dipole going in that direction, right? So the carbon is going to attack this carbon so you can form that 5-member ring. What do you think happens to the electrons in the pi bond between carbon and nitrogen here?
it breaks.
Yeah, but you break the pi bond and you give those electrons to nitrogen. You can see that right here, right? So you attack this carbon and then the pi bond, those electrons go on to nitrogen and you make this 5-member ring, right? All of this stuff we learned we either learned it here in this semester or in part 1. It's a polar mechanism. If you remember, you got 2 types of mechanisms, right? Polar and radical. The double bond had a dipole, right? Where one part was partially positive, the other part was partially negative. It's heterogenic bond formation and heterolytic bond cleavage, right? And then it's also, you can point out the nucleophiles and the electrophiles in each step, right? So all of this stuff, it looks complicated, but a lot of it is basic organic chemistry. It's just being able to recognize that, right? So this is the final part, one of the final steps to the synthesis of that cocaine final product, right? And let's just look at one part of this step. Look right here, right? You see you have a hydroxy ester that's here. And then over in the product, you have a double bond. What do you think? How do I get double bonds? Like what, out of the 4 different reaction types, substitution, elimination, addition, and rearrangement, which one of those always results in the formation of a double bond in the product?
Will it be elimination?
Elimination, right? Again, another basic reaction that we studied. How many, let me not ask how many because there's always multiple types, but what types of elimination reactions have we studied this semester?
Like E1, E2?
Yes. We've studied the E1 and the E2. Now, what if I told you that DBN, you should be able to tell me what that is because we've seen it already. But what if I told you that DBN was a strong base? What type of elimination do you think that is?
E1.
E1 doesn't require a base. Remember, it follows the same path as SN1, where your leaving group leaves first. But E2 needs a strong base, right? So this is going to be an example of an E2 reaction. Now, what if I told you that the mesyl chloride, MsCl, that's this right here. That's what you call a mesylate, right? We've seen tosylates, we've seen triflates. This is what you call a mesylate, methane sulfonyl chloride, right? All that is to make OH a better leaving group because we can't eliminate with the OH as it is because it's a horrible leaving group. That's something we studied this semester. Is that right?
Yes.
Right. When we did alcohol synthesis, alkyl halide synthesis from alcohols, the first step in each one of those reactions, we learned 3 reactions. We learned phosphorus tribromide, we learned HX addition, and then thionyl chloride addition. Every one of those reactions, we had to do the same thing first, which is turn OH into a better leaving group. Every one of them. And so the mesylate that we make is just for that purpose. We want to make OH a better leaving group, right? So if we add mesyl chloride here, right, that's just going to give you it's a simple, like a substitution type reaction. Well, it's actually not. It's an addition elimination on this, but you'll get the mesylate right here, right? You can see that now it's O, and then you have the sulfonyl part over here, right? Now we can use DBN to do our elimination and put that double bond in. All right. Anybody got a question about that? Again, this is all chemistry that we know. We know how to do E2 eliminations. We know that we can't eliminate a hydroxyl by itself, that we have to turn it into a better leaving group before we can eliminate. We know all this stuff. It's just now having to put it together that kind of seems intimidating, right? But if you look at that proton, even the proton that's next door to the mesylate, what functional group is this right here? Remember I told you if you see CO2, whatever, R, it can be any R group, that's a ester, right? So do you think that's going to play a role in making this proton more acidic?
Yes.
Yeah, because if you pull that proton off, if it's next door to a carbonyl, what can it do to be stabilized? Let's see. All right, if you have that's crooked, sorry. If you have a carbonyl like this, and you got a proton adjacent to it, and I'm just using my mouse, so it's gonna be sloppy. Right? And you remove that proton with a base and get, hold up. I wish I had a touch screen computer. That'd be so much easier. Man, it might be my Christmas present to myself. Right? Let's say you had that after you deprotonated. What can that anion do being next door to a carbonyl?
Basically, leave. You talking about what you just said?
Because
you removed the hydrogen.
Yeah, I already took it off. So what can this do, right?
Can it do resonance?
It can do resonance. Good. It can do resonance. I can take this pair of electrons and push them here, like that. And then boom, I can take that pair of electrons and push them there. That's a stabilizing factor. That's why the pKa right here is 14.2. That's not great, but it's not trash either. And with a good enough base, you can remove it. And so that's what happens, right? It's the conjugate base of this is stabilized by resonance. So boom, DBN can come in, grab that proton, boom, and then boom. So then you'll have an E2 elimination to put that double bond in, right? So this is all stuff that we've done before and that we've seen before. So it's not mysterious, right? And this is what the overall final step would look like, right? Where you just treat that with mesyl chloride first and then DBN, and that'll give you this alkene, right? So let me, yeah. So this is another natural product from the Japanese sea sponge. It's called plus 13 deoxytedanolide. The plus right here has to do with its optical activity. It's either going to be plus or minus. And this is one stereoisomer of this deoxytedanolide. You can see right here, you got a bunch of stereo centers, right? You got, let me see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 chiral centers. And again, if you think about this, right, this stereoisomer is the one that exhibits anti-tumor activity, right? The minus probably doesn't. So again, when you're synthesizing this molecule, it needs to be this, right? It can't be some other stereo. It can't even be a distereomer of this. It's got to be this stereoisomer. If you had to draw a distereomer of this, what would you do?
Flip everything.
Speak
If
up.
everything has dashes, I will make it wedged.
How many?
How many dashes will I turn into wedges?
Yeah, that matters, right?
8.
So you would change 8 of them. Okay.
Oh wait, no, diameter you change 1. You right. So you'll
Okay.
change
I just want to make sure I've been teaching something.
My bad. Yeah, you changed 1.
Yeah. So let me ask this question. How would you know how many different stereoisomers of this existed? How would you know that? Can you calculate it?
Yes.
I would think so. Yes.
Yeah. You can calculate it. I heard somebody say, yeah. How would you calculate it? Anybody remember? Got the final coming up.
It's 2 to the n.
2 to the n, right? And n is the number of stereoisomers. I mean, start a number of stereo centers. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 stereo centers. So it'll be 2 to the 11 number of stereoisomers. Do you see how much more impressive it is that you can isolate this or synthesize this by itself without any other however many millions of stereoisomers that are possible, right? That's why you need specific, talked about earlier, synthesis is using specific reactions to reach a target outcome. That's why you need specific reactions, right? But let's look at these reactions up here, right? You have a double bond right here, and you treat it with osmium tetroxide and NMO. We learned that in part 1. It's a dihydroxylation. And then if you treat it with sodium periodate, you can cleave it and cleave off. It'll actually cleave right here, right? And then boom, so it'll convert both of these sides into carbonyls. So you can see here, this gets converted to an aldehyde. And then what's not shown is the aldehyde that you'll get from here. It'll be like, it'll be a formaldehyde, right? And then there's also another step in here where you do a hydroboration oxidation. Y'all remember that reaction? That was like the first reaction even we talked about this semester. We were doing pre-existing stereo centers. So you take 9-BBN, which is a hydroboration reagent, and then you do hydrogen peroxide and sodium hydroxide. You can see right here, you can take this alkene, right, and turn it into this alcohol. What's the difference in using hydroboration versus using oxymercuration? Anybody remember? This is stuff from part 1.
Well, are you adding hydrogens versus adding oxygen?
Both of those methods convert alkenes into alcohols, but one of them is Markovnikov and one of them is anti. Right? Hydroboration is anti-Markovnikov, meaning your OH is going to come end up on the less substituted carbon in the double bond. All right, let's see what else we got. Let me clear this off. All right, this is another reaction, right? And this is a coral extract and has cytotoxicity against leukemia, against lung cancer. A lot of what you'll find out is a lot of your organic synthesis the targets are always going to be something that's bioactive, right? It's always going to be something that shows some type of bioactivity, either antifungal or anti-cancer, right? So this is the target, right? And then the way to get to that target, or one of the steps to get to that target, is deals all the cycloaddition. Can you see that? This is the 4 part, the diene, and this is the dienophile, right? When you react those together, this is your product, right? But it doesn't stay that way. The oxygen right here makes this an enol, so it's going to rearrange to get to the keto form. But you can see it again. Every reaction that we've looked at up to this point, we've studied somewhere along the line in organic, either in part 2 or part 1, right? So there's a lot of chemistry that we looked at, and also not just a lot of chemistry, but a lot of basic reactions that we've learned already, right? That are used every day in labs all around the world to do amazing things and build these amazing molecules that save lives, or that add to the body of chemical knowledge. That's everyday. That's our everyday thing, right? And that's why it's important to make the connection between what we're studying on paper and working examples and doing problems. We need to also recognize that there is a practical application of that stuff too. So I think that's the last slide. So I'm gonna stop right there. Any questions about anything we talked about?
They're uploading that PowerPoint as well.
Yeah, I will. I'll upload the PowerPoint. Yep. And then I've recorded this, so I'll upload the recording as well.